Yeah, hi everybody. Welcome to your Lecture 6 skill check. Here we're going to look at an example where we're going to use a chi-squared test to test for homogeneity. So let's look at this scenario. The question is, are all responses to 1E4 equally effective? Now, just to be clear what I mean by this, you might recall that in the Lecture 5 skill check, what we talked about is an example where after white makes their first move, pawn to e4, this is king's pawn to king's pawn 4, there are a number of ways black can respond to that first move, and each of those ways corresponds to a different defense. And so here we have a list of defenses. These are categories. So here we have a single categorical variable, which is the kind of defense, and then we have 6 categories of defenses. Right. So in the last lecture, we were asking something about the proportion of times players in a local club will play these different defenses. Here, it's a different question. Here, we want to know which of these defenses are more or less effective. And by effective, I mean with these defenses, are there any of these defenses where black wins more frequently? Right, so are all responses to 1E4 equally effective? So to explore this question, here we have 300 games randomly selected from a database of millions of games. And here we record the number of times black wins and the number of times black loses. So here, it's a chi-squared homogeneity test. Let's make sure you're clear on what that means. So in this kind of test, you're given counts across one categorical variable drawn from 2 or more different populations. So these data, these counts, they are reported in a contingency table. The null hypothesis is that the distribution is the same for all populations. So the thing to remember is, for a homogeneity test, we have one categorical variable. Here, the categorical variable is the defense. And we have a sample drawn from 2 or more populations. So in this case, for each defense, we took a random draw. Each defense corresponds to a population. So the first question is, are the conditions to perform a homogeneity test satisfied? So let's just review quickly those conditions. The first one is the data must be counts for different categories. And here, obviously, we do have counts. We have the wins and losses for each defense played. Second, the data must come from a random sample. So this is true, of course, for all statistical tests. And part of the reason we want randomness is we want independence. We want to make sure each observation is independent from all the other ones. But furthermore, taking a random sample is meant to maximize the probability that the only systematic difference between each of our observations is the thing we're interested in. So, for example, if I take some games at random, let's say I take games where the player with the black pieces plays the French defense. If I take a bunch of games at random, I need to know that the proportion of times the player with the black pieces wins or loses can be attributed to the opening, to black's choice of defense. What I don't want is a case where the main factor determining who wins or loses is the relative strength of the two players, right? So in other words, I want to make sure that in my data, in my sample, there are no systematic differences in the strength of the two players across these different defenses. I want to make sure that the only real difference between my random sample from each of these populations is just the defense played itself. So we're looking for systematic differences in the defense played, systematic differences in the probability that black wins. Without having those differences in win and loss probabilities being influenced by systematic differences in playing strength. Right, so if I could just try to make that a little bit more clear. For example, it's possible, when I take my data, it's possible that in this sample of 75, let's suppose I don't take it randomly, but I only select certain games. It's very possible that in all of these games, the player with the white pieces was the stronger of the two. And then likewise, let's say in the second sample, it could be that the player with the black pieces was the stronger of the two. And so in that case, if there's a difference in the probability that black wins, some of that difference is due to differences in the relative strength of the two players. And some of it is actually due to the differences in the nature of these two defenses. Some defenses might provide black better chances than others. So I want to make sure that if there's differences in the probability that black wins, it's not due to a systematic difference in the relative strength of the two players, but only to differences in these defenses. That's why we take a random sample. We're hoping that on average, if there are differences in the playing strength, sometimes the player with the black pieces is better, sometimes the player with the white pieces is better. If we take a random sample, that effect should be about the same in all of our samples. That's the purpose of randomization. So this sort of is a callback to, I think it's chapters 9 and 10 from 2208, where you talked about experimental design and how to take samples, how to set up an experiment with a control and a treatment and so on. It sort of harkens back to that. So anyways, I think I said enough about that. So let me just go back. So the conditions are satisfied. We have these two conditions. We have categorical data. We have a random sample. And the last condition is probably the one you're most often going to need to check or that you're going to be asked about. And that is that the expected count must be at least 5 for each category. And note, that's the expected count, not the observed count. We'll talk more about that once we calculate those expectations. Right, so next question. What are the hypotheses for this chi-squared homogeneity test? Well, the chi-squared homogeneity test, we are testing whether the probability of winning is the same across all defenses. What I mean is the probability that black wins. Let me just correct that. The probability that the player with the black pieces wins is the same across all defenses. That's the question. And so the null hypothesis is that all those probabilities are the same. The alternative is that they are not the same. Next, we need to calculate the expected counts for each cell. So this part is the most complicated. Now, I just want to emphasize that in a test situation, a midterm or final, these calculations you're not going to need to do. But I'd like to show you how these calculations are done, because my hope is by seeing a bit of the mechanics, it will help you understand how the test works and exactly what it's all about. So let's have a look. We're going to calculate the expected values under the null hypothesis. So let's just be clear. The null hypothesis is that no matter what defense black chooses, the probability of winning with the black pieces is the same. That's the null. The alternative is that the probability of winning depends on which defense is chosen. So under the null hypothesis, all these probabilities are the same. Right? Under the null hypothesis, the probability of winning with the black pieces is the same across all defenses. And remember, when you conduct a hypothesis test, you always start with the assumption that the null hypothesis is true. So that is actually very convenient because it gives us a very easy way to calculate the expectations. If the null hypothesis is true, then the best estimate for the common probability of winning is given by the marginal distributions. In other words, the best thing we can do when we assume the null is true, we can pool all the data. We can calculate the total number of times black won, the total number of times black lost out of the total number of games. So in this particular case, the best estimate we have for the probability of winning is 158 wins divided by 300. And again, this probability is consistent with the null hypothesis, which we are assuming is true. And that's why we can use this probability. So how do we use this probability to get the expected counts? Well, let's have a look. The expected number of times the player with the black pieces wins out of 75 games. So we're talking about playing the king's pawn opening, right? So out of 75 games played using king's pawn defense, the expected number will be the probability of winning. This is the common probability which we're justified to use because we're assuming the null is true. That's the probability of winning, and this is the sample size. So what we're saying is, if we take samples of size 75, and if the null is true, then on average, this will give us the expected number of times black will win when playing the king's pawn opening. And so now, the sort of purpose of explaining all that is so you can understand why the way you calculate the expectation is you just take the column total, you multiply that by the row total, so 158 times 75, and you divide by the grand total. And again, just to be clear, the column total divided by the grand total, that's the probability of winning with the black pieces. The row total is the sample size. So in this particular case, the expected number of wins when black plays a king's pawn opening in a sample of size 75 is 39.50. Remember, this number, 39.50, is a long-run expectation. It's an average. So we say on average, with samples of size 75, we expect to see black winning this many times with the king's pawn opening, assuming the null hypothesis is true. So now the point is we can calculate the expectation for all of these cells. So let's just look at one or two of these just to make sure you understand. So I'm going to pull out my calculator. So let's look at the Sicilian defense. So here, for the Sicilian defense and black wins, how many wins do we expect to see in a sample of size 97 when black plays the Sicilian, assuming the null is true? Well, we just take the column total, which is 158, times, for that defense, the row total, the sample size is 97, and then we divide by the grand total, 300. And so you see you get 51.09. That's where this number came from. Right, let's just do one more just to sort of drive in the point. So let's just pick something else. Let's say Scandinavian, black loses. What's the expected number of times black will lose when playing the Scandinavian defense in a sample size of 23, assuming the null is true? We take the column total, which in this case now is 142, times the row total, 23, and divide by the grand total of 300. Right, so now for this one, this was Scandinavian, black loses. The observed count was 11. It's right here. And the expected count, if the null is true, is 10.87. Right, so I know it's tedious, but I encourage you just at least once to go through these calculations by hand. And again, it's to help you understand exactly what is going on in this test. Okay, so let's just continue now. Enough with the tedious calculations. I'll leave that to you. So what's next? Right, so we want to conduct a hypothesis test. The way to do that is to first specify what your decision rule is. So we need a critical value for the test. So here, the thing to remember is that when you conduct a homogeneity test, the degrees of freedom comes from the size of that data table, of that contingency table. It's the number of rows, or you can think of that as the number of categories, or the number of populations. Remember, each of these rows represents a different population. So rows minus 1, and then columns minus 1. So here we have two outcomes in this case. So columns is 2, rows is 6. In this case, the degrees of freedom is 5. I want to emphasize, and somebody asked this question yesterday, emphasize that with these homogeneity tests, we always have to have at least 2 categories each category representing a population. So here, the population of games where black plays King's Pawn, the population of games where black plays Sicilian defense, and so on. So we always have that. Now, the number of outcomes doesn't have to be 2. It could be any number of outcomes. So tomorrow, you will see an example of that. Well, you're probably not listening to this on Wednesday, January 31st. So yeah, tomorrow may not be the same for you as it is for me. But in any case, at some point in class, you're going to see examples of a homogeneity test where there are more than 2 categories, right? So there doesn't have to be only 2. Okay, having said that, let's just go on. So let's get to critical value for the test. We're at 5 degrees of freedom. We want to conduct a 5% test. I guess that's what I specified in the question. And so the critical value is right here, 11.07. So we're going to use this now to set up our decision rule for the test. And it's simply this. We will reject the null hypothesis at the 5% level of significance if our test statistic is greater than that critical value. So easy peasy. All we have to do now is calculate that test statistic. And so here for this exercise, I ask you to do that calculation by hand. You could also have used Minitab, or maybe an Excel is a good way to do the calculation. In any case, we'll have a look here. The thing to remember now, the really key point to all of this, the observed counts are what we saw. The expected counts are what we would expect to see on average if the null hypothesis is true. And so where does the evidence against the null hypothesis come from? Well, the greater the difference between what we would expect to see under the null and what we actually observe, the bigger that difference is, the less likely it is that the null hypothesis is true. And so that distance we can calculate. It's called a statistical distance. It is our test statistic, all right? Our test statistic is a measure of the distance between what was observed and what we would have expected to see on average under the null hypothesis. Right, and just to drive that point home a little bit further, remember that, of course, we will always see some differences between expectation under the null and observation. The question is, are those differences just due to sampling variability, or are they due to something systematic, meaning the null hypothesis is not true, the assumed distribution is not true? So anyway, having said all that, how do we measure these distances? We take an observed value minus an expected value, and then we square that. So we're taking a sum of squares of deviances, differences between what was observed and what we expected to see. So let's just get the calculator out here. So in the first instance, we have an observation. We have 45 games won minus what we expected under the null hypothesis was 39.5 games won. And we take that value and we square it. And then we divide by the expectation. So here the expectation again is 39.5. So we divide by 39.5. We get the expectation. So I'll just take, see 4 decimal places. It's that. If I just go back a step, I guess I was going to also fill in the squared value, the difference squared. So I'll just do that again. 45 minus 39.5. I think it was 5.5. Oh, that's squared. 30.25, yeah. Oops. What's going on here? Right, so that's kind of small, geez. Boop, boop, boop. Okay, right, so this in the end, what does this number represent? It's the contribution to the chi-squared statistic made or attributed to this first difference, the first observation. Remember, when we calculate these measures of distance for each individual observation, we're going to just add them all up in the end. And that will be our chi-squared statistic. So let me just do one more to make sure everybody gets what's going on here. And so in the second case, our observed value was 48. The value we would expect to see on average, if the null is true, is 51.09. There it is. We square that number, so it's 9.5481. Just pop that in here. And then to get the contribution to the chi-squared statistic for this observation, we divide by that expectation, 51.9. And we get this number. It's going to be rounded to 0.1840. So we just plop that in. Right, and et cetera, et cetera. So these, it's a bit tedious to do the calculation, but it's not so hard. It just takes a bit of time. The thing to do, though, when you're doing the calculation is to, in your mind, always be thinking about what you're doing. You're calculating the contribution to the chi-squared statistic for each of these observations. And you need to remember that the bigger these differences are, the less likely it is that the null hypothesis is true. In the end, we're going to add up all of these differences, and that will give us our chi-squared statistic. It will give us the statistical difference between the observations and what would have been expected on average if the null hypothesis was true. Okay, so here are all of those numbers calculated. There's a tiny chance I might have got one of these wrongs, but in the end, we're going to validate this outcome with Minitab. And I just say that because I know when I'm doing tedious calculations, I'm very prone to make little mistakes. But I'm quite sure this is right, as we will see in the end. In any case, each of these numbers represents the contribution to the chi-squared statistic for each observation. So some of them are very small, some of them are relatively large. When we add all of these up, we get this statistical distance. This is the statistical distance between what we observed and what we expected to see under the null hypothesis. So now that we've calculated that chi-squared statistic, we can go ahead and draw our conclusions. So we go back to the decision rule. The decision rule was if our test statistic is bigger than this critical value for a 5% test, then we reject the null. So clearly, we are not going to reject the null hypothesis. We cannot reject the null at the 5% level of significance because our test statistic is less than the critical value. So what does that tell us? Well, what is it? It tells us, I had something planned for this and now I'm confusing myself. Let's go back. Let me just go back and see if I can gather my thoughts. So we're not rejecting the null hypothesis, right? So remember the null is that the probability of winning with the black pieces is the same for all defenses. Now, I just want to emphasize a little sort of subtlety when it comes to hypothesis testing. And that is, even though we did not reject the null hypothesis, we also didn't prove it. We didn't prove that the winning probability is the same for the player with the black pieces across all these defenses. All we really did is we demonstrated that there's not sufficient evidence in the data to say that that is not the case. So this is a bit of a subtlety. In the end, we really can't say for sure whether the null is true, or for that matter, when we reject, we can't say for sure whether the alternative is true, because there's always a chance of an error, right? So we can make a type 1 or type 2 error. And so we never use the strong language, we proved that the null is true, or we proved that the null is false. We avoid that kind of language. And so in this case, we cannot say that we proved that the probability of winning with the black pieces is the same for all defenses. But what we can say is that the data provides no evidence that the winning probabilities are different, right? So that's just a subtlety that I wanted to sort of rehearse with you. Yeah, so I guess I don't need to say any more about that. Let's estimate the p-value for this test. So we're at 5 degrees of freedom. And the thing to notice is that if our test statistic was 9.236, just by some chance, then the area to the right of that number is 10%, which means the p-value, if this was our test statistic, the p-value would be 10%. But look, our test statistic is further to the left, which means the area in the tail is definitely bigger than 10%. So we know for sure that the p-value for the test is more than 10%. And remember, of course, the bigger the p-value, the less evidence you have against the null hypothesis. So in this particular instance, the evidence against the null is, we're going to say it's none. It doesn't mean the null is true. It's just saying we haven't found any evidence to say it's not true. Right, so now that's all of that. We're pretty much done with the analysis. The last thing I want to do is show you how you could conduct this analysis in Minitab. And why show you this? Well, let's say on a quiz or maybe an assignment, if you're in a situation where you do need to do some calculations and you don't want to do them by hand, then it's nice to know how to use Minitab. For that matter, in another course, you might have an opportunity to actually use a test like this. And so it's a good idea to know how to do that. So the first thing to show you is how the data is set up. So here we have the defense. We have our categories labeled. And then we have black wins and black loses. So here, is that loses or losses? Anyway, win and loss, we have the data in this little table. How do we analyze it? We go up to stat. We go down to tables. And then we pick, tables. And then we pick chi-squared test for association. Right, so in Minitab, there is no chi-squared test for homogeneity. There is a chi-squared test for association or independence. But the point is, the calculations for the test for homogeneity and the test for independence, those calculations are the same. And so we can use the same function here. So we're going to use chi-squared test for association. And I should mention, it's possible that you don't yet know what the independence test is if that class hasn't happened yet. But by the end of the week in which I am speaking, you will have seen all three of these chi-squared tests. We have the goodness of fit test, which was skill check 1. The test we're looking at now, the homogeneity test, which is skill check 2, and skill check 3 for this chapter will be the independence test. Anyway, so let me just get through this so I can stop talking. So see our selection here. We can either plug in raw data or we can plug in a table. So you can see here the data that I'm showing you here, showing you here. It's already in a table, so I'm going to choose the option where I'm going to use data that is summarized in a two-way table. It says here the columns containing the data. So we have black wins, that's 1, and black loses or losses, that's 2. And then we have the option of putting in the column with the labels for each of the categories. So that's the one I call defense. So I put that in, press OK, and voila, it's as simple as that. We get all of this output. So this is giving us basically the data table with the expected values included. We'll look at that in a moment. And it gives you the chi-squared statistic and the p-value for that chi-squared statistic. So let's just have a quick look at that. Whoops. So notice that the test gives you a Pearson test statistic and also a likelihood ratio. You never have to worry about likelihood ratio. That's a different statistical method. As you can see, it's slightly different. It's always the Pearson one that you're looking at. This is the test statistic for 6.43. Our test statistic that we calculated was 6.42. So minor differences due to just differences in the way that Minitab rounds compared to the way that I round it. So that's not to worry. The p-value, that's interesting, it's 0.267. So all we concluded was that the p-value was more than 10%. Here we can see how much more. It's nearly 30%. So a very large p-value. And in the table here, I want to show you the parts of it. Let's make this a bit bigger. So we have here, hopefully you can see that pointer. We have here in these places, those are the observed values. These decimal values below each one, that would be the expected value under the null hypothesis. And you can see from our list of expected values that Minitab calculated the same values. So for example, in the first instance, observed was 45, expected under the null 39.5. That's the same as what we got. So we have observed, we have expected, and then in the margins here are those totals down here and here. Those are the marginal totals. So the row totals, the column totals, the grand total. So this is how you look at the table. It could be on the midterm or on the final. You're actually given a table like this, and you're given the results of a test and asked some questions about it. So you need to be sure you know what all these numbers mean in this table. Let's see, anything else do I need to say? I guess that's about it. So that's my explanation of the chi-squared homogeneity test. I hope you found that useful. We'll be talking about this more in class at some point, or perhaps we did already, depending on when you're watching this. I think now it's time for me to stop talking. So thank you for listening. Don't forget, if you have any questions, you can put them into the comments. I can address them either through comments or we can talk about it in class as you wish. Yeah, and that's it. So thanks for listening, and bye-bye.